So you have a choice. $1,000 a day, or you can start with $1 and double it every day for 20 days. What do you think would be the best choice? This one's a lot of money, right? How much money? Well, how much would that be? We just start with $1, and then the second day you'd make $2, and the next day you would make $4, and then $8. That can't. Which one's the better choice? My first period picked that one. Well, if you get paid $1,000 a day for 20 days, you would, of course, get $20,000. And I made a chart here of the other one. Start with $1 and double it and double it and double it and double it. And after 20 days, you have over $1 million. Is that surprising that it could go up that fast? This kind of equation is called a linear equation. It's what we have been doing. Oops. It's what we've been doing this year so far. Everything that we've done has been linear. That would be the equation that represents this. Now we're going to look at a new kind of equation that represents what's happening here. Well, what is happening here? It's doubling. Does that mean that the equation would be 2x? Well, let me show you how to get Desmos to help you figure that out. So on Desmos, y equals 2x. And then I'm going to hit this little gear right here and a table. And I want my table to start with 0. I don't want negative numbers right now. Does this table match the table I was just looking at? I don't think so. And I can't find what I need from here. Well, that table didn't match this one right here. That's not the right equation. Well, what's the equation going to look like for this? Well, what's happening right here? What am I doing each time? Am I doubling it means what? Add, subtract, multiply, or divide. Multiplying by what? I'm multiplying by 2 times another 2, times another 2, times another 2. When we times by the same number over and over and over again, that's when we use exponents. So let's look at this equation instead. This equation on Desmos, click back over to your Desmos, and let's start over. Y equals 2 raised to the power. I use my keyboard to do that. Shift 6 and then the X. You can also, down here at the bottom of Desmos, you can click on this down here. Let me get my Y equals 2. And you can also use this button down here to get the same thing. But I want to look at the table. And starting with 0, 1, 2, 3, 4, 5. Is this the table I had up there on the other screen? Let's check it out. 2, 4, 8, 16, 32, 64. 2, 4, 8, 16, 32, 64. This is the table. This is the equation that matches the table. This is called exponential because x over here, x is the exponent. So far this year, as I said, we've done linear equations. What do you do to get from here to here, or from here to here? Are you multiplying or adding? Adding what? And this is counting by ones, so this is our slope, 5 over 1. And so this equation is y equals 5x plus 0. What are we doing here to go to the next part of our equation? Our table. We're adding 3 each time. This is counting by ones. So this would be y equals 3x plus 1. That's what we've been doing so far this year. We've been doing a linear equation. Now we're going to look at another kind of equation. Do I add to get to the next number each time? She said I'm multiplying by 5 each time. You all agree with that? Okay, check it out using Desmos. Is this the equation that goes with that table? Do you know how to check it out in Desmos? Put it in Desmos. Y equals 5 raised to the power of x. You get this by putting shift 6 in your computer, and then it looks like that. And then you get a table that looks like this. Except Desmos may start with -2, and you can make it start with whatever number you want to. Does it match? Does it match? Okay, hold on. So what's the equation that's going to go with this table? What am I multiplying by each time? So y equals 10 raised to the x. Does that match this table? This number here is my multiplier. I'm multiplying times 10, times 10, times 10. This number is called my base number because it's the base of the exponent. What is my multiplier here? So what's my equation? If I'm multiplying times 3 each time, what is my equation going to look like? Is that the right equation? You ready for a tricky one? What's my multiplier each time? What am I multiplying by? But did it match this time? Not quite. What am I going to have to do? This one, go back. Come on, computer. This one was y equals 3 to the x power. And this is 2, 3, 9, 27. This one also is multiplying by 3, but it doesn't start with 1, it starts with 2. So, what do I need to do? No, I don't want to change the equation, not the table. If I add 2, does that match it? Did you check? Nope. If I multiply by 2, does that match this table? Did you put this in Desmos? Does that match this table? Okay, does this match this table? We all agree? 2 times 3 is 6. Is this equal to that? Put this in and see if it matches this table. Because of order of operation, you cannot multiply the 2 times the 3 and get a 6. Order of operation says you have to raise it to the power first and then multiply it by the 2. You cannot multiply the 2 times the 3 and get a 6. Okay, what's my multiplier here? How do we find the multiplier if we don't know what it is? We take the 1875 and divide by the number in front of it. We take the 375 and divide by the number in front of it, because dividing is the opposite of multiplying, and so that gives our multiplier. Now, is this y equals 5x? Does that match our table? No. But we know that the multiplier is 5. But what did we start with? And so we have to have a 3 number here to start with. Does this match my table? Uh-oh. What are we doing here? To go from here to here, what are we doing? You know that 0.5 is a half? What are we doing? Dividing by, let's start here. 4, 2, 2, 1. What are we doing? Except we can't divide, we can only multiply. So, this would be multiplying by a half. Doesn't multiplying by a half have the same effect as dividing by 2? And this is multiplying by a half. Our multiplier number is a half. And when our multiplier is less than 1, these numbers are not getting bigger this time. These numbers are getting smaller. So this is called a decay equation, because it is getting smaller. The numbers are decreasing, so that's called a decay equation. And the reason that I like this unit that we're starting here that's called exponential equations is because there's all kinds of real life examples of exponential equations. Exponential growth occurs in many real life situations. The water hyacinth which experts say double every 5 to 15 days, was expanding across Africa's Lake Victoria. This is a real thing, a real lake, a real thing that happened. This is out of a newspaper. This plant, it's a foreign plant, it wasn't native to the Africa, has taken up more than 769 square miles of the lake, and it's growing exponentially. Plants like the water hyacinth grow and spread rapidly and can affect the native plants and fish. It can start killing off the fish. And here is what is happening. Suppose we had this lake, this 25 million square feet. Is that a big lake? Huge. 1,000 square feet is covered by a plant, and it's doubling every month. Write and explain the equation. Exponential equations have this form, where this is the initial amount. What's initial mean? Well, you have an initial, right? The initial is where in your name? At the beginning, right? That's what initial means, at the beginning. And this is my multiplier number. So, how much of the lake is covered by the plant to start with? And what's my multiplier number? What's the plant doing? What number goes with doubling? So this is the equation. This is how much I start with. 2 is for doubling. Now, some people in my last class asked me about the parentheses. Here I put the parentheses around the 1,000. I think when I wrote it previously, I put the parentheses like that. The parentheses is just showing multiplication. It doesn't matter whether you put the parentheses around the 1,000 or the parentheses around the 2. It means they're multiplied. And you cannot multiply the 1,000 times the 2. This is not equal to 2,000 raised to the x. That's not the same thing. Okay. So, how much of the lake will be covered in 1 year? Well, here's the equation. It's doubling. This x stands for every month. How many months are there in a year? So, put this in your calculator, or your Desmos. How much? Now, if you have it in the table, then you just put the 12 in the table. You don't have to do the whole table. Just put in the 12. No? Okay. Okay. 4096. Okay. Now, square feet. Okay? And yours said 4.096 something times 10 to the 6th power. Depending on which part of Desmos you use, it put it in that way or that way. What happened? Do you recognize that as scientific notation? Y'all have done scientific notation previously, right? Probably in science. 10 to the 6th means 1,000,000. So this represents 4 million and this represents 4 million. It's 2 ways to write the same thing. Whichever way you write it, that's a lot of plants covering up the lake. Another example of exponential growth is mold. You ever had any moldy bread? Well, this biology class set a pan of chicken bouillon, chicken broth, out, and they recorded the mold. And the students wrote this equation for the mold. Well, what does this equation mean? What does this equation have to do with the mold? Okay, here's the equation. What's the area of the mold at the beginning of the experiment? How much mold did we start with? Can you tell from the equation? This number right here tells you how much you start with. And the previous screen told us that was in millimeters. So that's how much we start with. What's the growth factor? How much is it growing? Times 3 every day. D stands for day. So, how much mold would I have after 5 days? How do you calculate that? That's how much we started with. That's my growth factor raised to the power of 5. Put that in Desmos and tell me how much that comes out to equal. 12,150? So we started out with 50 millimeters, and after only 5 days, we have over 12,000 square millimeters of mold. That's growing pretty fast, right? I think, okay, this is back to the one about the lake. I think we did that one. Okay. Okay, I noticed when I went to Galveston that there were a lot of brown pelicans. There did not used to be brown pelicans in Galveston when I was a kid. But now there's a lot of brown pelicans. Well, I looked it up, and in 1960, the brown pelicans were almost extinct. They were native to Galveston. There were lots of brown pelicans around when my dad was born and raised in Pasadena, and when he was a kid, there was a bunch of pelicans down in Galveston, and then something started killing them off until they were almost extinct. But then the Texas Wildlife made an effort to try to get them back and try to protect them, and so their numbers started increasing. So, what is the increase? What is my multiplier to go to the next number? How do you find the multiplier? Pick a number and divide by the number that's in front of it. What's my multiplier here? Anybody got a multiplier for me? Pick any number and divide by the number in front of it. Did you get a 1.5? How many pelicans did we have in 1960? That's what I'm using for my starting point. This is the equation that represents how many pelicans. We started off with 16, and we had a multiplier of 1.5. This is how you put it in Desmos, 16, 1.5 raised to the power of x. So, here's my equation. raised to the power of x. Now, if I start out at 1960, how many would I expect to have in 1980? How many years is it between 1980 and 1960? So that would be 20 years. So how many birds would I expect to have in 1980? A bunch. Good grief. I can't even write a number that big. Oh, no, there's a decimal point in that. 53,000. I didn't see the decimal point. 204 or 2? And so there was a decimal point in there. Can I have decimal point birds? No. So if there's a decimal point, we're talking about birds or animals, we round it off to a whole number. And so after 20 years, there would be about 50,000. Now, in populations like pelicans, they may not continue to grow exponentially. They may have something, some kind of other animal that eats them and kills off some of the population. But the equations that we are looking at are called exponential equations. Exponential equations have the form, and this is my initial value, and this is my multiplier, and the multiplier is sometimes called a growth factor. This is the kind of equation we're going to be looking at, not y equals mx plus b, but y equals abx to the first power. Now, I wanted to go back to these that we started with. There's no, now, what I just wrote on that other screen was y equals ab raised to the x power. What's the a in this equation that we were looking at way back at the beginning? But when you multiply by 1, does it make it bigger or smaller or stay the same when you multiply by 1? So when my a value is 1, a lot of times we don't write the a value. If there's no a value written, that means the a value was 1. So these are the kind of problems we are going to be doing on assignment number 36.